Okay, I'll start the webinar. So just a preamble for a couple things. If you have any questions, feel free to submit them via the questions function in GoToWebinar. These are the topics we're going to cover today. I'm not going to be conducting this webinar using PowerPoint. I'll be showing you the actual software as we go through each of these measurements and functions. And if you have a question, feel free to submit that question at any time via the question feature. I will either try and answer them in real time or will address them at the end of the webinar. Having said that, just so everyone's aware, this is being recorded and we will share the recording and you'll be able to view it later. So with that said, let's hop over to APX 500 software. Okay, I hope everyone can see APX 500 software up and running. So just as a little explanation of what I have physically connected, you may actually see it in the background here and my stack of gear. I have a 2-channel automotive style Class D amplifier connected to my APX 555. You don't necessarily need an APX 555 to measure this device. It's just the analyzer I had at hand. In today's demonstration, I will be talking about this entirely in what we refer to as sequence mode. Those of you who have some familiarity with APX 500 may be familiar with this drop-down control in the upper right-hand corner of the software that toggles between what we refer to as bench mode and sequence mode. Bench mode is a little bit of a more advanced topic, so for today's demonstration, we'll be doing this entirely in sequence mode. And I've actually already got this up and running, but I'll just show you from sort of a starting state how we get going. Got the software up and running, so I'm going to go to File and just start with a new project. And I'll just select our standard template. Here it's just asking me if I want to save anything I was already doing. Okay, so now I have APX 500 software connected to an APX 555, which is in turn connected to my power amplifier under test, just in a default condition. So for those of you, again, with a little bit of familiarity, I'll just give a quick overview of our basic software paradigm here. In the upper left-hand corner, we have what we refer to as the measurement navigator. And I want to point out that this is a list that starts at the very top with what we call a signal path and then contains the measurements we're going to make on our device. The first node in this list, and the first place we're going to start, is called signal path setup. And the operational model for the software, which is pretty uniform in sequence mode, is I'm going to make a selection in the measurement navigator. So for example, right now I'm in signal path setup. In the middle pane are all the settings and selections I need to make for this context. And moving further to the right, we have results. Now, if I make a bit of a circle and I look down at the bottom of the software at our status bar our status bar tells us some informational things. Right now it's telling us what our physical output configuration of the analyzer is, what the physical input configuration of the analyzer is. Occasionally useful, what is our input range? We're currently AC coupled and going to a 90 kilohertz bandwidth, and we don't have a second input active. Coming around to the bottom left, we have what we refer to as the input signal monitors. This is a handy function. Actually, in this situation, it's a particularly handy function because you're not in my office with me and can't see what I physically have connected. What this is showing me is a continuously updating FFT spectrum of what's present at the physical inputs of the analyzer. I can look at a time domain or oscilloscope style view. I also have just handy level, distortion, and frequency counter type views. I do have some additional functions in the input signal monitors, but those are a little bit beyond the scope of today's presentation. So I'll just leave it at the default, which gives me a view of the input spectrum present at the analyzer. Now, all good measurements need to start in signal path setup. This is where we tell the analyzer how we're physically connected to our device under test. For today's program, it's pretty straightforward. We have an amplifier with an analog audio input and an analog audio output. And in this case, the input to the amplifier is balanced and its output is balanced. And if I just scroll down a little bit in this function called verify connections, I can turn the signal generator on. And you see we now have a signal present at 1 kilohertz. We're looking at the output voltage. If I wanted, I could switch to my oscilloscope style input signal monitor and see a nice sine wave. This gives me sort of instant verification that everything is up and running. Now, if you wanted to and you were a little constrained with screen real estate, I can, for example, undock different elements of the user interface. For example, this verify connections control. If I click on this little symbol that looks like an arrow popping out of a box, this will give me a full view of this signal generator. And just to fill this out again, I start on the left, I pick my element, I configure it in this middle pane, and then here in signal path setup, I can look at the output level of my device under test. Here is a view where I show the RMS level of the AC plus DC signal. This result is currently unavailable because our input is AC coupled. I'll show you that again in a little bit. We can look at the gain. So this is the output level divided by the input level, or the gain of our power amplifier, nearly 30, a little in excess of 30 dB. Here is the THD+N, total harmonic distortion and noise, and a frequency counter result, and then a couple results that don't apply in this context where we're looking at just an analog device. Now, while we're here, it might be helpful to look at a couple other features in signal path setup, primarily under references. So we are going to look at testing a power amplifier today. And one thing, a couple things that can be quite handy here, I'll undock this, is in this panel, we have our output references, and we may look at that in a little bit. But I'm going to go all the way to the bottom here of our input references. And nearly here down at the very bottom is this watts reference. So I'm testing a power amplifier, and I am providing a test load for that power amplifier. I don't have a speaker connected, but I do have a pair of non-inductive resistors connected, and they're 4 ohms. And I can type that value into the software here. And if I now go to my level meter, up here in the top of the graph where we have a few different controls available, I can select this unit drop down. I could still display this in dBV if I wanted to instead of volts. But one of the units we have available for display here is watts. Now, as I think some of you may be guessing, this is not a power meter. So we're not actually measuring the power coming out of the amplifier. What we're measuring is the voltage. But I've told the software that I have a 4 ohm load connected on the output of the power amplifier. And that 4 ohm load needs to be electrically in parallel with the inputs of the analyzer. And the system will just do the calculation of Ohm's law to tell us that the voltage corresponds, in this case, to about 3 watts into 4 ohms. I'll look at some additional references in a few minutes. But what I have now is I'm successfully connected the output of my analyzer to the device under test, verified that I'm getting a signal back from the device under test. Everything is working, and we're now ready to make some measurements. So going back to the measurement navigator, by default, it's going to have the 6 measurements we consider that are most commonly made on most analog types of systems. And we'll start with perhaps the most fundamental, our level and gain measurement. Now, again, the paradigm is the same. We're going to start here on the left, pick an element, a measurement in the navigator. In the middle pane, we have any parameters that are important for configuring this measurement. And then further to the right, we have our results from this measurement. In the middle here, for our generator, we can select some different waveforms. I'm going to stick to sine, the amplitude, and the frequency, and we can turn that generator on and off. Now, this is going to look very similar to what we just saw in signal path setup, and you may be wondering, why do I have a separate level and gain measurement from what I have available in signal path setup? One of the critical things to understand when we're testing power amplifiers, and in this case, when we're looking at the output level of our power amplifier, is we may want to verify this relative to different references. So when I say references, I mean, for example, we might want to test the amplifier at full gain. We might want to test the amplifier at 1 watt. We may want to test the amplifier at almost, or say minus 1 dB to full scale. So we can have multiple measurements in the measurement navigator, and each measurement will have its own unique settings. Now, level and gain is a pretty simple example, but I'll talk about that in detail a little further on. But this is a good place to just get started with the paradigm. We select the measurement, we configure it. In this case, we have an RMS level result. Again, AC plus DC. This result is not currently available because we are AC coupled on the input. I will return to that. The gain of our amplifier, and we add a result here that we didn't see in signal path setup. This is the peak amplitude of the signal. So this might make a bit more sense. I'll circle back to our input signal monitor, and I'll select the time domain result. If I undock that, so the RMS level is the average level of this waveform. It's the area under the curve, or a term I really like from the way the British describe this, it is the heating power of the voltage into a given resistance. And you'll notice that the peak amplitude exactly is what is the maximum voltage that it reaches, positive or negative, whereas the RMS is not the peak, it's the average level or amplitude. Let's go to the next measurement in the list. Let's look at THD+N, or total harmonic distortion and noise. Especially for power amplifiers, this is a very common figure of merit. Let's turn our generator on and look at some of these results. So the first result we have here is the total harmonic distortion and noise ratio. So there's a bit of a divide in the world. There are the people who prefer to express this as percent, and the people who prefer to express it as a dB ratio. Either way, what this expresses is the percentage or ratio of the energy at the output of the device that is not desirable. So in this case, we're currently stimulating the device with a 1 kilohertz sine wave. We can see that in the oscilloscope view here. What might be handy is to look at the spectrum view. Maybe we'll undock that for a second. And if we look at this as an audio spectrum from 20 hertz to 20 kilohertz, here at 1 kilohertz is our test signal, but we can see that there's actually a lot of other energy at other frequencies emerging from the output of the device. We clearly have significant power supply hum at 60 hertz and its multiples. Then we have some odd harmonic distortion at 3 kilohertz and 5 kilohertz. And then there's just noise. So all of this stuff, which is not our 1 kilohertz test signal, makes up approximately 0.18% of the energy at the output of the device under test. If we looked at this next result, this is the THD+N level. So this is not the ratio. What this tells us is what's the absolute amplitude of all the noise and distortion at the output of the device. It's currently about 6 to 7 millivolts. Now we can further parse this. Here is the ratio of the energy at the output of the device made up just of harmonic distortion products. Here is the amplitude of just the harmonic distortion products. Here's the ratio of the noise here is the amplitude of the noise. So right now, you can see that if we compare the noise level to the THD level, the noise level is most of the total harmonic distortion and noise. And the last couple of results here. So here is the ratio of the individual harmonic products, the second harmonic, the third harmonic, and so on. Here's the absolute amplitude of the distortion products. The next measurement we'll look at is frequency response. And here you can see a bit of the paradigm of the audio precision software. So now we no longer have the single amplitude and frequency signal generator. Here we want to measure the response of the device across a range of frequencies. So we have a start frequency, a stop frequency, and an amplitude. And I can select start. And now what we have is the absolute amplitude response of the device as a function of frequency. So here's the RMS level. Here's the gain of our device. Here's the relative level. So here we've normalized the frequency response to 0 dB at 1 kilohertz, and you can see how the device rolls off. And finally, over this frequency span, what's the total deviation in response? We're going to circle back through these measurements and expand on them a bit, but if you have any questions, feel free to submit them as we go. The next measurement we'll look at is signal to noise ratio. So a little bit different. We pick a frequency and an amplitude, and if I select start, what we arrive back at is a ratio in dB. And in this case, what the analyzer did is it measured the idle noise of the device. Then it measured the output level with the signal generator on, and then gave us a ratio of the two. So this is, again, a very classic figure of merit for power amplifiers. Now, some of you might be wondering, well, how did I choose the voltage level that I tested this device at? And actually, in this case, I didn't. This is just the defaults in the software. I'm going to circle back to this in just a second. But just to explain, this measurement, signal to noise ratio, is just telling us the ratio between the idle noise of the device and its output when we stimulated it with the signal we chose. The next measurement we're going to look at is crosstalk. So again, if I select start, here what the system is going to do is it's going to generate a signal in one channel and measure how much of that signal leaks into the adjacent channel. We're testing a stereo power amplifier. We all appreciate stereo signal imaging. So ideally, a device will not leak too much between channels. What this does is it tells us when we drive actually channel 2, channel minus 60 dB of that signal leaks into channel 1. When we drive channel 1, minus 50 dB of that signal leaks into channel 2. The next measurement we're going to look at is interchannel phase. Now, In the case of this particular device under test, what we're measuring here is the time alignment between two channels. And this is one where it's helpful to look at the oscilloscope view. So what we want ideally is for both channels to be aligned in time. And I'll just make this frequency a little higher. And if we zoom in, it's actually a very good device, but you notice they're not perfectly in phase. In fact, at 20 kilohertz, channel 2 is 1.5 degrees ahead of channel 1. This is definitely not a problem, but this is what phase, or in this case, interchannel phase is measuring, is what's the time alignment between our channels. And again, the human brain uses time alignment phase between our left and right ears as one of the ways to figure out directivity of sound. So it's relatively critical in an audio system to have controlled time alignment between your channels. And that's what we measure in the phase measurement. Okay, now let's circle back and talk about our level measurement for a second. So right now, I am stimulating the device with a 100 millivolt signal. I'm getting 3.5, 3.6 volts out of the device. Since I provided my resistance of the resistors I'm loading the amplifier with, I can also see that I'm currently getting about 3 watts of power from the device. Is this the level I want to test the device at? Maybe I want to test the device at its full power. What is the maximum power we could get out of this amplifier? Now, I could do this a few ways. One way of doing this, I'll say a kind of old-fashioned way, is I could start increasing my output level. And you'll notice that at a certain point, it starts to clip. And the reason people would use that clipping term is we look at the peak of our waveform, what's happening here is it's actually running into the maximum voltage of the power rail supplying the amplifier, and the peak of our sine wave gets flattened out. And maybe I'd sit here and manually adjust the signal generator level till I'm satisfied I'm just below that point. This is a perfectly valid method. If we went back in time a number of years, this is absolutely how it was done. You'd drive a power amplifier with a signal generator while looking at its output on an oscilloscope. You can see we're getting pretty close to 100 watts out of our device. If we look at the FFT monitor, you can see also the device is clipping fairly significantly in terms of the prominence of the second and third and other harmonic products. Now, another way to do this that can be quite convenient is I'm going to go back to signal path setup. And I'm going to go back to my references. Maybe I'll expand this a little. And for my output references, I'm going to select auto gen level or automatic generator level. And it's going to bring up this sub menu where it's going to offer to automatically set the generator level by regulating THD+N ratio. And conveniently enough, it's set to a default of 1%. So I'm going to say I would like to find the generator level at which my power amplifier has 1% or less distortion. I'll stop when one of the channels has the highest value, and I'm going to do it by adjusting the generator. Now you do want to use some care here because we are going to drive a power amplifier. You could accidentally destroy your DUT. So I'm going to put a start and a stop value somewhere in the range of where I think it's going to find that value. I'll go fairly broad. I believe that it will find that value between 100 millivolts and 1 volt. And now I'm going to select start. And once it's finished, if I happen to look at THD+N ratio, you can see channel 2 is right at 1%. Channel 1 is a little bit below that. And we're getting just about 80 watts out of the amplifier. Now, the other thing you will notice is it's put the generator level that it found for this into this output reference value called dBRG. And if I go to verify connections and I undock it, and on my generator level, amongst the other units like volts RMS and dBV, we have this generator unit dBRG. And what I have done is I've asked the software to find the generator level that gives me 1% distortion at the output of my device under test, and then to set 0 dBRG to be equal to that. And it's a little bit of an old school definition, but exactly 1% distortion is classically defined as the maximum output level for an amplifier. Now, maybe you use 10%, maybe you use 0.1%, you can choose, but I'll use 1% for today. And now what I can do is I can go to, for example, my level and gain measurement, and I can say, let's measure that at 0 dBRG. And if I do that, I get 80 watts out of my amplifier. Now, if I go to THD+N, probably you don't want to measure this at full power. That's probably not going to be super interesting because, of course, by definition, this is very close to 1%. Maybe I want to measure that at something less than full power. So I'll measure it at, say, -6 dBRG. Frequency response, typically you want to measure this well below your maximum power level because you don't want to clip your frequency response. So I'll set this to -20 dBRG. For signal to noise ratio, This you almost certainly do want to measure at full power. You want to measure typically the ratio between the noise of the device and its maximum output level. So I'll use 0 dBRG as the reference. And on a classic basis, we're looking at a 90 odd dB signal to noise ratio. For crosstalk, we typically do want to measure this at full power. So we'll measure this at 0 dBRG. We'll probably get a similar result. And then interchannel phase, doesn't matter too much what your output level is. You probably don't want to clip while you're making this measurement, so I'll make it at -6. Okay, so now we sort of have the, I'll say, 6 most fundamental figures of merit for this amplifier. So what I'm going to go ahead and do is I'm going to check the report. I'll go ahead and check each of these measurements that I'm interested in. Maybe for frequency response, I just want the relative level result. And maybe for THD+N, I just want the THD+N ratio result and my output level. And now I will run this sequence. And so now what I have is a report of each of these measurements, how the system is configured for the measurement, and the actual results of the measurement. Now, before we conclude, let's just talk about a couple more measurements, especially in the context of a power amplifier. We often want to know about the response over a varying level of amplitude. So I'm going to select Add Measurement. This is a relatively long list of all the available measurements in this software. I'm going to scroll all the way to the bottom, and I'm going to add my stepped level sweep. And let's do an amplitude sweep of this device. So for my start level, I'm going to say I want this in dBRG, and let's start well below maximum power. Let's start -60 dB below maximum. And let's go somewhat over. Let's go 10 dB over. And let's do this in steps of 1 dB. So when I start this measurement, the system's going to generate a 1 kilohertz tone, starting at -60 dB below full scale and going to 10 dB over full scale. And the first result is going to be the generator level versus the RMS level. Again, the AC plus DC results not currently available. Here's our gain. So we should see ideally constant gain across the amplitude regime. You might know that term as amplitude linearity. And let's take a look at this result for a moment. So here what we can see is at very low levels, the amplitude linearity is off, and that's because this is showing us that at very low levels, regardless of the signal we put in, we're getting a lot of noise out. When this flattens out, this is the range in which the amplifier is got perfectly linear results. because the signal amplitude we put in is the signal amplitude we get out. And then at some point we get to the voltage rails of the amplifier, and our linearity falls off because we keep increasing the amplitude of the signal we're putting into the device, but the device can't give us anything more. Another way we can see this is if we look at the THD+N ratio versus generator level. As we increase the generator level, the ratio is improving because more signals coming out of the device. Now, clearly one channel of our amplifier is a little bit wonky here, but the other channel shows us what we would expect, which is it keeps improving until we start clipping. So this is a very classic curve. If we look at it not as a ratio, but as a level, you can more clearly see what's going on here. Here's the noise floor of the amplifier. Then at some point, our signal is well above the noise floor, and then we go into clipping. Here's our THD, so only harmonic distortion, ratio and level. Now here is a result that's sometimes more typically desired. So this is the total harmonic distortion and noise on the x-axis, but on the y-axis we have the measured output level. So this is how much voltage we're getting out, or if we wanted to, here is watts of power versus total harmonic distortion and noise. Here it is as the THD+N level. Oh, sorry. So this tells us how our amplifier behaves across a range of signal amplitudes. Now, maybe we want to see all of these things across a range of frequencies. So let's go ahead and add a measurement. And I'm going to add stepped frequency sweep. So here we're going to vary the frequency of our test signal while the amplitude of our signal is constant. So let's do this at, say, -6 dB below full scale. So the first result here is the frequency response, the same thing we've seen before. Here's the gain and the relative level and the deviation. Here is the interchannel phase across frequencies. And if we auto scale this, you can see a little tiny deviation. THD+N ratio across a range of frequencies. Here we can clearly see channel 1 is a little bit wonky. Channel 2 has a more typical result. THD+N level, just the harmonic distortion, just the noise, and so on. Now, all this time I have been omitting discussion of DC. DC is undesirable in the outputs of a power amplifier, typically, but is a figure of merit. We typically want to minimize it. So let's add the DC level measurement. So now you'll notice at the bottom of the screen, our input bandwidth is DC to 90 kilohertz. And here we can clearly see something's wonky with channel 1. It's got a pretty significant DC offset, especially compared to channel 2. Probably been damaged somewhere in its history. And if I wanted to, if I go back to signal path setup, in our input configuration, if I scroll down, I can change my high pass function to DC, and this will DC couple all the measurements. And so, for example, here is the AC plus DC measurement, where again, I can see that there's a significant DC offset in channel 1. Now, just because it's such a common question, I want to specifically talk about Class D amplifiers for a second. So I'll expand, I'll do 2 things here. While I'm in signal path setup, this is an APX 555, so our measurement bandwidth does go up to 1 megahertz. And if I undock the FFT monitor, and I'll auto scale the frequency axis, this is in fact a Class D amplifier. And what you can observe is up here to about 20K, you don't see anything, everything looks fine. But we have a bunch of stuff from the switching frequency of the amplifier, which is actually quite high in amplitude. Here at, what is that, about 300K, we've got about 500 millivolts, 400 millivolts actually, I can see it right here, from the switching fundamental. And we do make a product, or actually I should say a family of products for this specific thing, our so-called AUX switching amplifier measurement filters. I have one handy right here, and what we can do is I will physically bring them into the circuit. And exactly what these do is what this filter does is it attenuates this out of band energy that can adversely affect our measurements. Okay, in the last 10 minutes here, I'm happy to entertain any questions you may have. Feel free to submit your questions. So good question here. Do I recommend any specific tests for amp configurations like bridge mode? So the measurements, or if you prefer, the figures of merit for different kinds of power amplifiers are fairly universal, I'll say. But what is very relevant is, I'll go back here to signal path setup, and I want to talk about the input configuration specifically. So in the old days, most power amplifiers were single-ended devices. That is to say, there was a terminal referred to ground that contained the signal. Much more commonly today are differential or bridge mode amplifiers, where you have two terminals swinging relative to each other. If you plug a bridge mode amplifier into a single-ended connector, and on APX analyzers, your single-ended connectors are your BNCs, you will hopefully just current limit your amplifier because you'll be driving one side of the bridge into ground. So hopefully your amplifier has a current limiting function and it will just stop. But in the bad case, you'll short one side of your amplifier into ground and it will burn itself out. So if there's any ambiguity about the output configuration of your amplifier, just always use the balanced inputs on your APX. That's the main thing I'll say about different amplifier configurations is when in doubt, use the balanced input. That way you don't potentially short one side of your amplifier to ground. Another question, is it okay to measure in dBRA? Absolutely. So for example, let's just take a quick look at that. I might go, well, I'm here in signal path setup. Let me expand. I'll turn my generator on, and what's being referred to here is if I also bring up my references panel, I'm currently stimulating the device with a signal that gives me the full scale output, and I am going to set my input reference. Let me set my input reference to 17.72. So now if I go to my drop down for my measured result and send it to dBRA, what it's telling me is how many dB relative to the full scale output. And that can indeed be quite useful. So for example, if I go to my level and gain measurement and express it not in watts, but in dBRA, it's telling me I am 0 dB relative to full power, and that should be linear. So if I go and change this to -6, now I'm -6 dBRA, and so on. And then the next question is, would you also recommend the use of power spectral density measurements for an amplifier? Yeah, let's take a look at that. It's a little bit of a more advanced question, but we have a little bit of time available. So I'm going to add another measurement, and I'm going to add what we refer to as signal analyzer. And if I, well, actually, let me start here. I'm going to add another measurement first, and I'm going to add noise RMS. So here, I'm not turning on the signal generator. I'm just measuring the idle noise of my device, 480 odd microvolts. And heck, maybe I want to measure this relative to my maximum output level. So you'll notice this looks an awful lot like our signal to noise ratio result. But regardless, what this meter is telling me is what is the amplitude of the noise in my system. If I wanted to know, well, what is the shape of that noise? this is where we might use Signal Analyzer. So in Signal Analyzer, we're going to produce the same view we have in our FFT spectrum, but I'm going to turn off the generator channels, or I can set this to 0 volts. That's another way to get there. Won't go too far into this, but I'll set an FFT length. And actually, let me go back and return my bandwidth to audio style bandwidth. And here is a spectrum of the noise of my device. Now, one thing you might notice, what happens when I change the length of my FFT, the noise, the level of the noise appears to go up and down. One way to avoid this, so this is an illusion created by the fact that an RMS scaled FFT is dividing the same amount of energy into more and more measurement points. Amplitude spectral density scaling avoids this, so it will show us the amplitude of our device regardless of the length of the FFT I choose. And this is a good view to look at that and see, well, what are the specific things, what are the specific frequency points contributing noise to your device? Damping factor, I'll just quickly cover that before we run out of time by saying that there is a specific utility on our website that you can download. It's no additional cost. If you search our website for damping factor, you should find it, and it will return the damping factor of your measurement. Okay, let me see if I am. Is there? Yes, there is a free trial of the software. First of all, you can download the software from our website and use it in demo mode to your heart's content. You can also request a free trial of our website, a free trial of our software from our website at that point. All right, just in the last few minutes, let me see if I can catch up. So at this time, you can only enter one reference value for the load, and it's used for all input channels. That's a good feature request. Yes, when I say RMS and average, that is redundant. We do not return S parameters. So the way to do a sweep of SNR across frequencies would actually be to do two sweeps, one with the generator on and one with the generator off. It's a little advanced for this, but if you contact our technical support team, they can walk you through that. So frequency response is, there are a few different types of ways in which it might be measured, but fundamentally what's going on is we sweep a signal across the frequency range of interest while measuring the output level of the device and just plot that. There's nothing too fancy going on. Okay, I think I have covered, well, let's see. You do not need a 517B to test power amplifiers. It's not a safety issue. A 517 is actually probably not the most appropriate choice for testing power amplifiers. Fundamentally, any of our analyzers can be used to test power amplifiers. You're just going to want to look at the input and output specifications for the analyzer to make sure that they're a fit for your amplifier under test. So if we do a frequency sweep, then the distortion curve is frequency dependent. If we do a step level sweep, it is level dependent. I am going to stay away from THD on loudspeakers. That is not something we're talking about today, but we may address in a future webinar. Intermodulation distortion, we are running out of time. I'm over time. It is a very valid measurement. It's a little bit of a more advanced topic we might cover in the future. We do not make recommendations on amplifier designs. We just make the tools for measuring them. So the difference between dBRA and dBRG. So dBRA is an arbitrary reference value for the input. So if you want to express measurement results relative to some value, you would set dBRA, or there is a second one, dBRB, to the value you want to be referred to. dBRG is a generator reference value. So if you want to set the generator amplitude relative to some reference value, you would use dBRG for that. We're out of time, so I'm sorry I'm not going to cover burst mode today. And unfortunately, we're not going to cover today either. We're not going to discuss Bluetooth today. And yes, if your power amplifier has digital inputs, SpeedIF or PDM or I2S, whatever, the measurements are really the same, The only difference would be in signal path setup, you would pick the appropriate output connector. The difference between the input and output load on the references tab, frankly, in all normal situations, I would only recommend using the input load reference. The output load reference refers to the dBu generator unit. dBu is a little bit archaic because it implies that you're testing a 600 ohm terminated circuit, and the generator reference refers to that. What is the generator's source termination? Very, very few people actually change their generator source termination, so I would recommend leaving that alone. So if, what about 100 volt output measurements? If we're referring to the output of the device under test, this is exactly where you'll want to refer to the specifications of the analyzer you're using. Now, having said that, almost all audio precision analyzers can measure 100 volts. The only analyzers that are not rated for 100 volts are the APX511 and the APX517. If you're testing a device that needs a 100-volt input, none of the audio precision analyzers will generate 100 volts, so you'd have to connect an external amplifier to the outputs of the APX to gain the generator signal to that level. And the webinar video will be available in the next day or two. Okay, I believe I've captured all questions. If there are any other questions, feel free to submit them. Otherwise, thank you very much for joining me, and we will be reaching out to you to send links for the video. Am I missing anything, Jen?
No, the only other thing I was going to say is that for anybody that wants to stay up to date with future online and in-person audio precision events, you can visit us on our website at ap.com/events, or you can also follow us on LinkedIn, our LinkedIn channel where we normally post things. But that's it. Yes, the video will be available tomorrow. We'll send an email out to everyone who registered.
All right, thanks everyone. Have a great day, and hopefully we'll see you at the next webinar.